So this is another episode 3 of Orbitals, and this is kind of going to be a concluding episode where we organize slightly etc. information about orbitals. So in normal conditions, as we mentioned before in the previous episode of electron configuration, they just all follow this rule. But there are some exceptions. Now, the first few exceptions are the excited state. So basically, when atoms follow the normal configuration pattern, they are called the ground state. That's the normal state that they are in. But if they receive energy, they become excited. And the excited state is basically if, for example, F9. Now, fluorine's normal ground state or normal state of electron configuration would be 1s2, 2s2, and 2p5. This would be normal, right? But if it receives energy, it becomes excited. And excited fluorine configuration is slightly different. 1s2, 2s2, but instead of 2p5, it becomes 2p4. And an extra one is added of 3s1. So what happened is that because this electron received energy, it moved from 2p, the orbital of 2p to 3s, which is another level. And this is because it received energy. And we just need to know that there are some excited states. So if there are some examples that do not follow the norm of electron configurations, just know that they are called the excited state. And excited state happens when they receive energy. Alright. And there are some exceptions that aren't excited configurations or are in excited state. And those exceptions are CR24 and Cu29, and we just need to memorize this. There is no pattern. These two are the only exceptions in the periodic table to the ground state norm of electron configurations that aren't excited state. And the configuration for CR24 chromium would be 1s2, 2s2, 2s2. Next we would go on to 2p6. Next we would go on to 3s2, 3p6. Now 4s1 instead of 2, and 1 would go up into D. And this would be the correct ground state. The correct ground state. And this is because it is an exception. We just need to memorize this. There is no other way to know except for memorization. And there are only two, so it's quite easy to memorize anyways. Now the correct configuration for Cu29 would be 1s2, 2s2, 2p6, 3s2, 3p6, and once again an electron from 4s, the orbital 4s, would go up to 3d, and instead of 3d9 it would be 3d10. This would be once again the correct configuration for ground state for Cu29. Last of all, talking about valence electrons. And when we count valence electrons, there are various ways, but if we are using these orbitals to count, only s and p are counted as valence electrons. So basically, D and F aren't counted as valence electrons. So only S and P are counted for valence electrons. Now, isoelectronic iso means the same, electronic means electrons. So isoelectronic basically means that a certain element or atom has the same number of electrons as another one. So we would call these XY elements isoelectronic. And an additional information to know about orbitals and electron configurations is that if there are ions exist, then we just add or subtract the number of electrons for the normal electron configuration. And that is everything that you need to know about orbitals and how to calculate electron configurations. And that's it for orbitals.